Presented by Caltech.
Okay, welcome back after this little break. We've seen quite a few interesting talks now already about the global methane budget, and then kind of the elephant in the room in terms of sources, which are wetlands, microbial emissions. Now we want to switch gears completely and have Michael Prather here from UC Irvine to talk about the opposite, basically the destruction of methane and what's happening to it in the atmosphere after it's being emitted. And with that, I want to, without any further delay, give the floor to you, Michael. Thanks for being here.
Thank you, Christian. So this shows my typical view from my backyard to Pasadena in the morning. We're about 60 miles away there. It happens every morning like this, no, but only if you get up early enough before the pollution rises and it's in the winter. Okay, so methane. Let's talk about methane. What's so hard about understanding and modeling methane loss? Okay, this is sort of one of the funny things that we discovered, played with, and whatever. This is just a model result of column methane loss, so it's not even individual layers. It's the column methane loss. You're looking at factors of 4 or so in neighboring parcels, and this is in the column. You're basically trying to figure out why methane loss, and this is probably a minimum compared to the real world. This is only running a half-degree model. You've got all this variability out there. You've got rivers of methane loss. It's not the same as the rivers of water. They're slightly different. And this is what we're trying to get at and integrate over when we basically run our 3D models, or we compare our 3D models with measurements. This represents probably one of the stiffest tests to think that you can represent the statistics of that kind of variability and then integrate it properly. So what do we need to know for methane calculation, for a top-down sort of calculation of methane lifetime, and what are all the hidden facts? Okay, so this was sort of what I was after trying to do when the last IPCC started up and was running, and I knew I had to do part of a chapter on lifetime and integrate production, integrate methane in the future. And so I started thinking about what does it take to know the numbers of methane, and it got me started on this little project, which is a bit crazy. Okay, and so the project was reactive greenhouse gases systematic exploration, and we'll look at it in a minute. But effectively, we sort of estimated what we thought was our best estimate of the methane lifetime, OH lifetime, total lifetime, and anthropogenic emissions versus natural emissions or whatever. So what does it take to do it? Well, if you think about what are all the hidden numbers that go into it, there are about 40 primary quantities that you really need to know if you're looking at methane, methylchloroform. In this case, we did HFC 134A as well as N2O. But these are all little sort of primary quantities. And what do they look like? They're about 46 derived quantities that we went through slowly, propagating the error as you go along. And it was a bit of a silly spreadsheet exercise, but it was sort of interesting there what you really need to know. One of which is the atmospheric mass. It's very funny how we really disagree on how much mass there is in the atmosphere. It's unusual. Most people have very odd results. Some are fairly typical. Since we're running more now full-up weather forecast models, the masses are much more consistent than they used to be. People used to be off by 3% in the total air mass, which certainly made a difference in budgets. And so we went through our model, which runs European Center forecast fields, and we had to dig up what was the air mass wet. So you see the air mass wet is right here. Then we had to figure out how much water there was, because we have to take out the water. Okay, you have to remove the water from the dry air mass because everything's measured by dry mole fraction, and so on. So you have to run through your model and sort of figure out what are the pieces. Other aspects, surprising things you don't realize are the fill factor. This is actually very important for doing it right. Okay, fill factor is this. This is from Dieter Eholt's old paper long ago with Ulrich Schmidt. These are profiles in the stratosphere. Literally, from your tropospheric mixing ratio, how much mass is in the atmosphere. This is very important because it controls the methylchloroform decay rate. If you don't have it right, you get the wrong decay rate compared to methane, because as methylchloroform gets eaten up in the troposphere, it actually comes out of the stratosphere. Stratospheric loss is slower, and you have to actually do that for the total budget to sort of figure out what are all the total masses. So once again, little things you sort of have to put together to get right. Pre-industrial values we tried to deal with. This is very important here. This is the ratio of the rate coefficients at 272K, which is what we started in 1990 and Clarissa redid. And the 272K is because most of the OH is sort of mid-trope, slightly above the cloud levels. It peaks. So it's about 272K is the transfer between two reaction rates. And the point is, Bill DeMoore is one of the few people who measured with flash photolysis the relative ratios of different rates. And it's the most accurate rate we have of methylchloroform to methane is more accurate than you get from the JPL tables, which most people use. And so you really want to use the relative rates that were measured, which are actually more accurate than the single rates. Global decay rate of methylchloroform, well, that's what it looks like from the Omanska paper in 2011. Okay, that's fine, we get that one. Various other things like change in tropospheric OH and feedbacks, pre-industrial. So again, Then you start doing derived quantities. What's the burden? How do you convert parts per billion with fill to actual mass content? Okay, and you go through the various lists. So anyhow, this was somewhat maniacal, but slowly managed to get through it, okay? And then you get down to the end, and you end up with various things like methane lifetime, N2O, okay, natural emissions. You come up with an estimate of pre-industrial present if you know the pre-industrial concentration, which we have uncertainties on, and propagate that. And then we have to estimate what pre-industrial OH was, which we have model measurement, model assessments, which we put an uncertainty on those. Nothing's perfect, but everything's listed straight up front in the spreadsheet, so you can argue any numbers, change them, and do the propagation. So it's a first order sort of test run, sort of top-down numbers. It's not necessarily the best, but it hadn't been done before, and nobody bothered looking at the details and the numbers of what you needed. So it was sort of fun, and I think it gave us a first order number. That doesn't mean we won't get better numbers when we understand methylchloroform decay rates, but to first order, this is fine. So what did this start? Well, it began, let's say, 1995, IPCC second assessment report, when we started putting in the methane feedback for the very first time. Okay, Isaacson and Hove here basically noticed that methane was increasing faster. When they did 10% perturbation, they got more than 10% increase in methane. I did an eigenvalue decomposition to show that it was timescales. We'll look at that in a minute, okay? And then basically we did a multi-model assessment, which actually looked at the methane feedback in a whole bunch of early models, very early models, 20 years ago. Got about 40% feedback factor. It hasn't changed much with the models. It seems to be a large integrated quantity over a large number of conditions. So it actually tends to be fairly solid for most of the models we've seen today. The third assessment report, 2001, came online. Again, fairly straightforward. Feedback factor 1.4 was established. Isaacson and Hove's was 1.3. That 1.4 has probably 1.3 to 1.5 is typically what most models fall in that range. So we have a fairly solid reliability of what the feedback factor is and what it does, and we'll look at what it means with that factor. That means that the global, everything that goes with methane increases by 40%. So it was the biggest change in any GWP that ever happened since the IPCC. So quick look update. This is from the scoping meeting in Addis a couple weeks ago. This is the next IPCC AR6. You probably have not seen this because it's not published anywhere particularly. Okay. It's good I didn't put the little bar numbers on it, which show that it's off my copy, and they'll track me down if I give out the copy. Right? This is the new outline. It's not approved. The governments will approve it in October, maybe September, October, November. The governments get together, the IPCC actually approve the outline and maybe revise it a bit. This is working group 1, and there are 2 chapters that are going to affect methane, so this is sort of informative issues is all. The 2 chapters you're going to see will be chapter 5, which is carbon budgets, biogeochemical cycles. Okay. There'll be an issue of methane sources, natural, historic, and variability issues. Be a fairly important source in that region, okay? It will be doing it from the issue of long-term greenhouse gas approach, okay? The chapter after it is short-lived climate forces and air quality, a whole chapter devoted back to chemistry again for a while. Again, this will be dealing with methane, ozone, and everything else from the point of view of pollution. These things are meant to deal with for the first time. Did they do it? Future air pollution, including cease? No, there's supposed to be extremes in here somewhere. They dropped it again. Both of these are dealing with extremes and propagation. So all of these 2 chapters are not the current state. They're actually taking the current state and running it to 2100. So we're actually having individual chapters looking at changes in air quality, short-lived pollution forcers, looking at extremes in air quality, and doing it from that point of view. The same way the biogeochemical cycles will be looking at high-latitude ecosystems and running those through. So that's potential for the next IPCC, which is due out in 2021, okay? This gets approved by the governments. They will probably change some things, but not a lot. So this is a fun paper. I just want you to look at it from the point of view of IPCC. I know I'm hiding it. I hate to hide things when you do this thing, but it's worth thinking about. This is the first assessment report. This is the methane plot that you've seen there. Okay, we've seen this one, go right there, okay. And this is what the first assessment report had to work on. So it's worth thinking historically about when we sort of took stock and started summarizing things, what was available. Okay, this one was the first report. Second report, oh, well, the first report was like almost the old 1% per year. The second report is like, oh, we got a little turn there, what's happening, okay, and this is what was put in the report and what they could do. By the third report, well, okay, we now have 2 different slopes. Third assessment report. Fourth report, we get the flat tableau, okay. Yeah, okay, what's that mean, okay. And then you go to the 5th report, it's coming up again. And the 6th report, it's gone up again. So it's a very interesting sort of history when you think about when you take stock and when you sort of write up your assessment of methane. It's sort of, you've actually had quite several different periods of understanding or of observations that would have changed the focus on the kinds of papers that are written and so on. And we've now seen a lot more papers written on understanding the hole wiggles on this one. Okay, so let's move on to something more obscure. Chemical modes, eigenvalues, and feedbacks, okay? So what do we mean by, there are three things I want to talk about. There's a loss frequency. Loss frequency has a 1/time unit. It's a hertz or whatever. It is a per frequency loss, first thing. You can think of that as a loss frequency. They tend to be local. You can have a mean loss frequency also. Lifetimes. Lifetimes are never calculated as loss frequencies. They're always calculated in budget terms. It's kilograms divided by kilograms per year. That's the way lifetimes have always been defined, and they're very useful to define that way, but you have to think of them as nothing to do with timescales. Then there are actually the timescales of the system. Timescales of the system are something else. That's what happens when you kick it, and that's how it responds. So if you want to think about the timescale of the system as you perturb it, and you ask, what are the ripples, how does it go through the system? They're very different, okay, and sometimes they overlap, sometimes they're very close, but you don't want to think of them as all being the same, because then you will get in trouble, okay? So this is an odd example, okay? This is the budget lifetime depends on the emissions and the abundance patterns, basically. The time scale does not. So let's look at this one on the budget lifetime. What I've plotted above is the methyl chloroform lifetime, basically loss frequency. That's a loss frequency per latitude belt. And I've pumped through the observed profile. So this is the loss frequency up here. That's from 0.1 to 0.3. These are the profiles. So this is 1992. This is 1972. And now this is 2000. And it's going down now almost constant the same way. If you take those four profiles, you get different lifetimes. Now, they aren't very big right now. They're about 1%. But if you had a short-lived gas, like methyl bromide, they'd be much bigger. Because what you're doing is you're redistributing the mass of your gas depending upon where you emitted it and depending on how close it is to the major sinks. And so the lifetime really depends upon your sources of emissions, or in this case, your long-term decay. And so it's a little small example, but the best I could come up with is where nothing changes in the atmosphere, but the lifetime of methyl chloroform changes. Okay? That's the budget lifetime. That's what happens, okay? So you have to realize that the lifetime is not people used to think the lifetime was a state of the atmosphere. It's not. It's the state of the atmosphere against the distribution of the species. So let's go through this quickly, but the idea. If you set up your differential equations to map out how you calculate something in a 3D model, you have transport, chemistry, radiation. You sort of put operators on all the species, okay? Then what you can do is basically do the partial, basically look at what happens to a perturbation, and the perturbation will then end up looking like the Jacobian down at the bottom here, okay? Whoops, times the perturbation. So the Jacobian is the linearization of the entire system multiplied by a perturbation, gets you an estimate of the DDT term. That is the rate of change of a perturbation. So if we want to know the rate of change of a perturbation of the system, we can calculate it by linearizing the system. Okay, let's go this. Okay, when you do that, effectively, if you have eigenvalues, you end up saying, gee, you can have an exact solution. Your perturbation has a pattern and a time scale. And almost all the things we've seen in atmospheric chemistry are negative eigenvalues. They all decay. There's sometimes there are chemical systems, BZ oscillators and everything, where they're positive, and you have states where things are actually amplifying for a while until they go to another state. But most of the things we see are negative values here. And so basically, any perturbation can be written as a sum of exponential decays where there's a pattern in front of it. Okay? Again, so you want to think about this one. So the chemical mode basically for any perturbation in a system operator is going to look like that. You have a sum of coefficients times an exponent. The coefficient will be all species and all 3D locations and all seasonal variations. So large interannual variability doesn't work. Rough interannual variability does. Recycling annual cycles, this works. Okay. If the years to year vary, these will be shifted a bit. Okay, they won't be exact. So what it means is that any perturbation can be decomposed into the modes, and so you want to really find out what your perturbation looks like in terms of these modes which have real time scales. So the methane originated from Don Fisher, 24 years ago, okay, in Nafius workshop, alternative fluorocarbons, environmentally acceptable substitutes. This is in old days of CFCs and ACFCs, okay. He reported a result that the methane perturbation he ran through a model because we're starting to get interested in methane and climate at that point, as well as other things. He found a funny behavior. The lifetime of the methane was 8 years in his model, but the decay was 12 years. and he had no explanation for it. He just put it up there and said, I really can't explain it. And everyone thought it was just, you know, do I have any more there? Everybody kept thinking it was just his perturbation was too large. He invoked some nonlinear systems and everything else. And so I talked with Doc C and we went back and puttered about and played with it individually and came up with a different approach. Different approach is actually, if you look at the methane system, and this is a toy model, which still reproduces what the 3Ds do, because it has the essence of methane reacting with OH, CO reacting with OH, carbon monoxide, and OH reacting with some other background. And then you end up with a set of 3 systems of differential equations. They're fairly straightforward. You can pick the coefficients and the fluxes to make them look like an average atmosphere. It's not perfect, but it works, okay? So there's the sources and the answers you can set up. So that's the systems in steady state. And now you ask what happens to a methane perturbation. Is you look at the Jacobian of the system, which is this, the partial derivatives of all the equations with respect to all the variables, okay? And it looks like this with real numbers. That is, you actually have to have the numbers put in to get the value. It's a nonlinear system, so the Jacobian depends on the species abundances. The reason why this thing is misbehaved is because of these things here. They're off-diagonal elements. The off-diagonal elements mean that the eigenvectors and the eigenvalues are not the diagonal components. If you have a triangular matrix, the eigenvalues are nice. They're all the diagonals. It's all the loss frequencies you think of. So these are the diagonal elements, 9.6 years for methane, 0.24, and half a second for OH. Now you'll notice that the half second for OH corresponds to this huge number, 10 to the 6th, and the methane is the smallest number down the diagonal because it's the inverse of the eigenvalue. Then you do the eigenvalues, and you find that you get one that's 13.6 and one that's 0.28. So it's slightly different. The smallest number changed the most, which is and that means the lifetime of methane changed the most. So we've gone from a 9.6-year diagonal term for the lifetime to actually 13.6 years for the decay of a perturbation of methane. And what's funnier is this is up here is the set of eigenvectors. So there's the 13.6 years, mostly methane, a little bit of CO, you don't see OH. The lifetime is 0.28 is mostly CO and some negative methane. And the eigenvector for OH is mostly OH with a little bit of the other ones. Okay? And so those are the 3 eigenvectors. Those allow you to decompose any perturbation into those 3. So what happens is if you look at a perturbation of methane that's 1, we take our big one here, we get this. And so we get methane 95% in the long, 0.5% in the short-lived mode, CO and everything else, and so you get the usual thing you would expect. Most everything is methane decaying at 13 years. You have 0.5% of methane in the short-lived 3-month mode. Okay, what's more interesting with this is the whole core of it. Now you put a perturbation to CO in, okay, and this goes counter to what we wrote in the first 2 IPCC reports that short-lived species could not have long-term impacts on the climate. Wrong. I put a perturbation to CO in, and what happens is I get a perturbation to methane, which after a few months gets me about a 15% molar perturbation, mole per mole methane per CO molecule. That's because the eigenvectors are all not diagonal, they're coupled, and so a perturbation to CO has to map onto all 3, and it goes onto the CO. And so what you end up with then effectively is, you've created with a perturbation to CO that seems to die off in 3 months, you've created a 14-year perturbation of methane at about a 15% level. Now, 15% is from the toy model. You'd have to look at better models to get the numbers. I'd suspect it ranges from 8 to 15 or 8 to 16 or something around that level. Okay, so the key issue is those off-diagonal elements in the Jacobian, the feedback of OH on itself on this other species, are what creates the behavior. Now, this was very controversial. I got yelled at and dragged across the coals by people at the IPCC meeting in '95, and the ozone meeting was right before it. They didn't like it. I got told to explain it. I said, I don't know how to explain it. It's just what happens, okay? Okay, so I tried and tried and tried. So finally came up with this one, and I could convince the people who didn't like the math, okay, that basically you have this snake down here. This goes way down here, 1750 baseline ozone. You put your added methane in, which we call a red, and then the green background methane increases because the red methane reduces OH. So it's sort of obvious. If you put in methane, it'll reduce OH. Now what it means is then the background methane pops up. And the background methane pops up in proportion to what I put in. So you don't notice that it's actually dead proportion. I put in 1% or 10%, I get proportional increase. And then effectively your red methane decays still with like an 8-year fold, but you have this funny little bump down here. Okay. is effectively your background methane that has just been popped up. That got through to most of them, but that sort of worked. So one of the interesting things is, why doesn't it work for 13-methane or methylchloroform? Well, it would if it did. I mean, if you had an equivalent teramole emission of those guys, you'd have a whopping impact on the atmosphere. But a 1% addition of methane gets me about 0.4% in OH. A 1% increase in C13 methane, because it's down by a factor of 90, gets me 0.0004%. So you don't see the change in the methane abundance, or even the change in the C13 abundance doesn't change because the OH changed by way down in there. Yes, you get a change at that level, but it just doesn't show up. And so once again, same with methylchloroform. I put in trace gases, I put them in. They will have an effect on OH. They are sink. But they're small enough that they don't really impact the whole thing because we're thinking of perturbations to sort of the whole background. So methane still wins because it's the elephant in the room. OK. What's wrong with using methylchloroform to infer tropospheric OH and infer methane lifetime? How accurate is the decay rate? OK, we have all sorts of questions. We've been seeing that's the hot topic these days. There's one problem I have in that this is serious. A lot of new papers continue to report the mean OH concentration. That's actually useless. It's totally useless because you have to know the temperature that that OH was sitting at in order to calculate the loss of any species. And so the mean OH, unless everybody has the same temperatures, and I've seen some model results that everybody's differs a bit. Why? Because the models have different temperatures. So even if they get the same OH, the lifetime versus OH is not the same because they have different temperature reactions. And the point is, you really need to report K times OH integrated, not OH. Because I don't care whether it's 1.06 times 10 to the 6 or whatever. It's a very convenient number, but I can't map that onto a methylchloroform loss unless you tell me what temperature it occurred at. And you have to assume that both models had the same mean temperatures and distributions. And it's one of the sort of bugbears. I don't know why people love doing mean OH concentrations, but it really just doesn't work. I mean, it's irreproducible. And you can see it when you have multi-model comparisons. People have different OHs, but they'll have the same lifetimes because the temperatures are different. So once again, we need to be more careful on how we do this. The methylchloroform decay is measuring this quantity here. The reaction rate coefficient is a function of temperature times the OH integrated over the globe. That's what's actually measuring. So Chris Holmes ran through a bunch of models. We tried to understand the methane lifetime and its variability that we saw the decay of. And this is a range of different models, GEOS 5, MERA, GEOS 5, Oslo, UCI, all doing exact simulation, Hindcast, 1997 through 2009, I think we had everybody at the time, that's several years old. And we're trying to understand how does OH vary. So what we reported on was the mean methane lifetime, okay? And you can see the models change from 11 down to 8. Our model's way too hot down here. It's way too fast for OH lifetime. Some of the others are okay. But the variability is remarkably consistent, slightly different. And a lot of that is just the physics of the atmosphere. You're changing El Niños, you're changing water vapor in the tropics, you're changing temperatures, slightly shifts, and are basically driving a different OH chemistry. All of them are trying to use GFEDs. They're all trying to use the right biomass burning signal. Lightning, everybody does their own, okay? Lightning Knox. But effectively, the models are running very different baselines. So you run huge from like 8.5 to 11, basically, which is sort of scary. That's sort of typical model range. If you look at the recent assessments for the ACC MIP, you get about the same answer. But effectively, these are actually fairly good in terms of following a certain behavior. Okay, that's how the atmosphere seems to be changing if we put in biomass burning temperatures and everything else from sort of a simulated or forecast fields. And then this is what happens when you plot them on top of the blue and the orange are the NOAA and the A gauge estimates. They're old ones, but they may have changed slightly. This is an estimate of methylchloroform decay anomaly on the right. That's the big shaded regions, 0 to 10, from plus or minus 10%. And this is the methane OH lifetime from the models, which would be similar anomaly, percent anomaly. And you see the models are very muted in their response. Even what seemed like large variations is actually pretty small variations. When you put in percent, it's just not that big. There is an interesting thing that the models are seeming down here to go to higher OH, lower methane lifetime. But this stops at 2009, so we really need to double check what happened since. So again, the models have a variability. It's much smaller than the observed variability. The observed variability shifts between who's doing the observing, which is worrisome, okay? They don't have the same, they don't agree on the same timing of the variability. That seems to be an observing system problem. We'll leave that to the observers to figure out what to do with. But again, you know, the measurements are so tight that do you worry about it? No. I mean, the fact if you're in the 3 to 5% range, that's probably about the best we can do for either the models or the measurements. But there's no clear correlation between given time periods. Okay, other tidbits. Coupling of methane and N2O. Nobody bothers noticing it, but it's all right. Nitrous oxide is one of my other favorite gases for a long time, like Lori's. Okay, and so we began long ago in 1998, many years ago, in the pre-paleo world, a 1D diffusion model for N2O and showed that basically the N2O has coupling like methane does, and the N2O basically does the other. It speeds up its lifetime. So the N2O lifetime is reduced because N2O in the stratosphere destroys ozone. Ozone lets more UV down. More UV fries the N2O in the middle stratosphere, and that actually reduces the N2O lifetime. So perturbation N2O is about 8 to 10% shorter than what you get from a budget lifetime. Exact opposite of methane in terms of directions. What we never got to do, and I always wanted to do, was to do the methane N2O together through the stratosphere and troposphere. And so this was done with a 1D model, and it took many years later before we actually got a 3D model to actually run, you know, multi-100-year simulations with perturbations and whatever, consistently sort of recycling an annual typical meteorology, and basically run through the methane N2O full 3D coupled chemistry. And what you get is some funny things, great things. So this is what happens if you throw in 10 teragrams of methane. Now the plot here is log, these are log plots. This happens to be the mole fraction at the equator. So we're looking in the stratosphere at 31 kilometers. And so what happens if you throw in 10 teragrams of methane is then you get basically this 12.5-year mode here decaying, and ozone goes with it, and then ozone reverts negative, and then N2O picks up way out here. So the problem is we're down about 4 orders of magnitude or 5, so you're actually seeing a fairly small tickle, but the methane is enough to tweak the stratosphere, and then you can pick up the N2O, the NOI in the stratosphere, and even the methane reverses in the stratosphere eventually. So again, an example of a fully coupled system is quite interesting. You have to it took several iterations with our model. Most models have irregular numerical noise that prevents this from happening. Okay, if you have unphysical changes in your species, you don't get this. It starts creating noise, and we even found that eventually. So it took us a while to get our model so it didn't make those things. More fun is if you put N2O in. This is now global perturbation in kilograms. So we're looking more at the troposphere, just the total content. Here is 10 teragrams of N2O. It decays with 108 years, approximately about 108 something. Here's methane. It pops up and goes negative. Dashed lines are negative. And so what you find is that the nitrous oxide basically perturbs tropospheric chemistry enough to change the methane and the ozone and so on. What's interesting about this is then the perturbation to methane in tropospheric ozone has a 108-year lifetime, not a 12 to 14-year lifetime. So the perturbation locks onto the N2O mode, and the N2O mode already has this ratio of there. And you notice it's actually fairly high. It's within an order of magnitude. If you put in CO, you can still have fun, okay? The CO decays quickly, and then you have the methane lifetime decaying here, and then eventually the N2O pops up a little later, but not too much N2O comes from CO. But you can even show that carbon monoxide in the troposphere tweaks the N2O. Now again, these are fairly far down. This is 5 orders of magnitude. And you'll note that down here, our model had some non-physical numbers in it, which created a difference between two things could not be held to like 5 places between 2 separate runs. But anyhow, so what does the budget look like? Nitrous oxide, 118-year budget lifetime, mode time scale 108. Methane in this model, this is not an analysis that we did before, this is just the model run. Our budget lifetime for methane was 7.8, and the mode time scale is 12.4. Okay. Again, typical. Most models have similar ratios. The numbers are not necessarily good. This number, I think, is pretty close to when we did analysis using MLS N2O at about 4 or 5 models. It's similar to the lifetime we got recently. And this one also, for the models that could run the perturbation to look at, is about the same. So one thing that's interesting is that if you look at the N2O climate impact, you have 8.4% less because the mode time scale is not the lifetime, budget lifetime, so you have to be careful. And then the coupling to methane takes another 5% off, basically. Methane is a negative impact. N2O reduces methane, so you further reduce the N2O sort of global warming impact because of the impact on methane. This has not been included. Nobody does it, but hey, It takes a while for things to sink. One of the more obscure conclusions, which is a little odd, and this has to do with understanding of how we release gases, where they get destroyed, what you do for timing and everything else, is that the N2O pulse has a mode amplitude of 10.2 teragrams, which means that it looks like 10.2 teragrams decaying over 108 years, not 10. Why is that? Because it takes about 2 years or so for the N2O release to get into the stratosphere where it's destroyed, and that means it doesn't get into its final pattern until several years, 3 years down the road, and effectively it looks like an extrapolation of 10.2. There was never 10.2 added in the atmosphere, but if you take that long mode and extrapolate back to 0, you'd have there's an extra 2% of N2O. This applies to all gases like CFCs and everything else that we do that are lost in the stratosphere. This is typical. There's always about a 2% offset. You have to be very careful on interpreting lifetimes and mode times. Okay? And effectively, it's just sort of uniform across the thing. Methane's the exact opposite. You're down a couple percent the other way because you put it in the troposphere, and more is destroyed faster in the troposphere than the stratosphere. So then it has to get in the stratosphere, and then it gets its pattern. So effectively, there are a lot of interesting, fun things to look at in terms of methane and ozone. I'm now in my 30 minutes, so I can quit dutifully. And I know you've had enough equations and whatever, but in fact, it's a real wealth of trying to understand how the chemistry of the atmosphere really works, how it distributes things between strat and trope, even northern and southern hemispheres, which are not always done well. There's a lot of box models out there that will be inherently different than the fundamental models. When you use the full-up 3D models, you'll get different times rates of exchange. You'll get gradients within hemispheres, which box models don't have. So there's a fairly wealth of material out there that sort of needs to be looked at well. And I think we're on the road to doing it. But again, there's a tendency to sort of forget. I think we're almost down to the 5% level, 5 to 10% level of trying to sort of do things. We don't have any large effects left. So I think we're down to sort of small scale effects. So if 2 or 3% worry you, it shouldn't, but as a bias, you don't want to have it. Thank you.